Okay, and welcome. My name's Gary Taylor, and we're going to look at service invocation as part of Dapr. So if we head off to the main website at docs.dapr.io, we can look at some of the quick starts, and one of these is service invocation. And if we go through this, we can see we've got this checkout and order process, some name resolution, some mutual TLS. Lots going on here, but not a great deal about what is the problem we're trying to solve. We can even see we've got a demo here that we can run through where there's an order processor and then some kind of checkout system that will connect to that here, and basically it's one API calling another API, and it doesn't feel very clever, but if you can look through the process, you can kind of see what's going on. But first, I want to talk a little bit more about the problem. So as part of a traditional microservice architecture, you can build an amazing system where a customer connects to your checkout process. Everything is clean, isolated, decoupled microservice architecture, and the world is good. And you have your databases that are completely decoupled from the rest of the service, and the checkout basically then goes to an order processor. The order processor then delegates out to a payment system, and then the payment system delegates out to a shipping system until eventually the customer has completed the order and shipping of a particular product is going on, and all this information goes back to the customer, and the spinner on the dial has finished spinning, and the browser refreshes and says, "Congratulations, you have just bought a PlayStation 5," and everyone's happy. But there's a particular problem with this. A common wording is one is none within IT, especially when dealing with cloud infrastructure, in that we have only got one instance of each one of these processes, and each process heavily relies on the other process to do its job. A customer can't complete unless the order process system is up and running. And the order processing system can't complete unless the order payment system is up and running, and the order payment system can't run until the shipping system is up and running. So traditionally back in the Stone Ages, when you would have one monolithic architecture, one big application, one database, well, you only need to keep the one thing running. And it's quite easy to keep one thing running in comparison to trying to keep four things and four databases running. If one of these things fails, you're done. However, the dream of microservice architecture, which I like by the way, is that if the order payment system starts to become slow, what we can do is we can say as a manager, order payment is too slow, make it fast. So traditionally, what we will do is we will scale out and we'll create multiple instances of that one particular microservice. So now here we've scaled out, we've got one checkout, it seems to be doing well, we've got one order processor, and now we've got three instances of the order payment. Because we said, no problems, microservices are built to scale. But the problem that we've got now is we need to get this into production. And load balancing three different services can become challenging. So let's go back to the Stone Ages where we create three separate VMs, we create three separate DNS records, and now the order processor's factory, let's say it's C# or whatever, it has a connection out which will then delegate responsibility between these three different services. And we figure out that it's not just the order payment system that's slow, we also have a problem with the shipping, but just not as much. So we only need two instances here of our shipping system. So now we have this one system to one system that connects to these three systems, which then can connect. So we have quite a complex chain of dependencies here, and each one, apologies, that should be order shipment 02, but you get the point, 1 and 2. But now the order payment system needs to be aware of the two different order shipment systems. The order processor needs to be aware of the three different order payment systems. So to get around that problem, generally what we'll do is we'll do some kind of Azure App Gateway load balancer magic, where basically there is a load balancer that understands these three IDs or IP addresses and delegates it under one DNS. So the order processor now hits the Azure App Gateway, and then the order payment system hits the Azure App Gateway. But that doesn't come for free either. That needs to be configured. These VMs need to be set up, installed, updated, maintained and supported, and the code needs to be delivered and pushed up and migrated onto these three systems either simultaneously, or hope to God that you've got a good blue-green deployment process. And if you don't even know what that is, then you're going to be in trouble. So the Azure App Gateway or any other kind of load balancer can facilitate managing these multiple systems. But let's say we bring it to modern day and we have some containers running on maybe Kubernetes or Azure container instances. We get IP addresses that we now need to supply as the app gateway. And as these things are torn down and torn back up again, they get new IP addresses that need to be updated within the Azure App Gateway. So we haven't got to a point now where, as a developer, we can just build our services and run. We now need to deal with cloud infrastructure and DevOps. So, okay, I have my app. I've built all these 4 or 5 services. Let's become a cloud certified engineer in order to deploy this. And of course, this is relatively expensive, getting these things up and running, maintaining them and supporting them. They're not free. So eventually you'll get a request of, the order payment system's quite expensive and we only need it for 5 o'clock during peak traffic. Let's tear everything down to just one instance during off peak. So now you have to implement some kind of provisioning of elastic resources that can turn these things down and put these things back on. Kubernetes does help with some of this orchestration and some of this delegation, but it's still not a magic bullet. Or a silver bullet, I should say. And of course, you may get to the point where you have security and compliance regulations, and they say to you, well, is this all locked behind your own personal VNet? Is the traffic controlled via ingress? Have you got SSL communication between all of these services end to end? And the answer would be, what? Sorry? And now you need to think about placing SSL on each and every one of these services. But luckily you decided to use Azure App Gateway, so you can do all the termination there. But then these systems may be intercommunicating with each other, which you can't have. So then everything needs to communicate with the Azure App Gateway. So you get this 3-way traffic of every service connecting to the Azure App Gateway, for the Azure App Gateway to then delegate it to the appropriate service and back again. And all that starts to get a little bit complex. Now here we have only got 4 microservices. Consider a system where over time, on average from my experience, even the smallest team can build microservices incredibly quickly. And I wouldn't be shocked or horrified if a small company would end up having maybe 100 to 200 microservices added every year. And that can soon get over a big burden with this type of architecture. So these are known common problems. And one of the ways of solving this is to make it so that the systems don't know what they're talking to. The checkout system will delegate requests to an order processor, but won't actually know where the order processor is. It will send a request out, and this may be done as events or as a call, and something somewhere will delegate that event. Something like maybe Kafka or RabbitMQ, if you've seen anything like that, or Microsoft's Azure event system, Event Hub. So the checkout raises an event and something subscribes to it and then processes it and maybe sends the results back. But that can be quite a challenging architecture and isn't actually technically a microservice architecture. It's more event driven. So if you're sticking with a microservice architecture, you need the ability for your checkout system to access an order processing system without actually knowing where it is. So what I've done here is I've drawn some soft lines, so you can see that the dashed lines, and that indicates that I, as a service, do not know how to access or where a particular dependency is. So let's talk about this from the top. We have a customer who typically accesses a load balancer, whether it be Azure App Gateway or Front Door. And that'll be some kind of UI that allows them to check out or view products and check out. And the checkout system will then delegate responsibility to an order processor, but it doesn't know how. It just requests it. And there may be multiple instances of the order processor. And all of this information is managed and secure over, say, for instance, mutual TLS, which is an encryption. And each one of these can communicate with a service which is not under load. So if these three things are at 80% CPU, then the next request is going to go to that system. And it may be round robin, and you can tweak how you want that kind of thing to work. Now, it wouldn't be great at, say, 2 o'clock in the morning that all of these systems just go down so there is just one of each. And as things start to get busy, let's say the shipping system starts to come under load, new services just appear and disappear. But the rest of the system isn't aware of how or where them things are. There is no manual hard coding of URLs or IP addresses or even domain names. We just say, call the order processor. Now, Dapr is not the first person to come up with this. This has been around for a very long time, and the ability to have service discovery has been in things like Spring Framework and things like that for a very long time. It's just the idea is now becoming more concrete, and .NET, traditionally late to the party with .NET Core, but doing a fantastic job recently, has now realized that it needs these toolings. But instead of relying on complex third-party software to try and implement these, or third-party libraries, Dapr, I think, has come up with something amazing and relatively unique. You know, sidecars have existed for a while, but I do love the cleanness and the idea of delegating responsibility. But what does that look like? Let's head off to a demo and let's have a play about it. So as we head back to the website, we can see there are a couple of examples in different languages, and I've tried all of them, and they're really good. They're really simple and easy to do. If we download and clone the quick start, we can then start to run through these steps. But what I've found is that the README files within these quick starts are actually super helpful. So let's use them instead. So we have got the README, we have got an order processing code, we need to restore and build. So let's give that a run. So that's cool, that's run. We have an order processing application that we have just built now. And what we can do is we can run this application. But instead of just running it as you would do with .NET Run, you can wrap this within the Dapr command line. So we're saying, as Dapr, please run this app and run it on port 7001. And I want you to call the app order processor. And the protocol we're going to use in this scenario is HTTP, but we could use something else like gRPC, which is a bit quicker because it's HTTP 2 and it's also binary format, so it makes it just a little bit quicker, or a lot quicker if you've got lots of services. And we're going to run Dapr because don't forget Dapr is a sidecar, which is going to be providing us with an API that sits alongside of application, and that's going to be running on port 3501. And then we just do .NET Run. So let's give that a go and let's see if that starts. So awesome, that started up. We are running the Dapr sidecar, and we can see sidecar, I call it cart, but sidecar, and we are good to go with the looks of that. So let's run our checkout system. So we build that. And then we're going to run the checkout system. We're going to give it a name, which is going to be obviously a different name. And we're going to give it a different port that this is going to run on so we don't get clashes. And now we can see that what's happening here is the checkout system is making calls to the order processing system. And after a certain amount of calls, it'll finish. But I've made a slight change here to this code. And what I've done is I've actually made it old school. What we can see here is that the base URL is basically got localhost 7001, which is what we run the other system in. If I can find the appropriate window, which is here. This service run, and I asked it to run on port 7001. Now that means that I need to know the URL and the port and the protocol that it's using. And if I need that to be HTTPS, that needs to be to HTTPS, which then can no longer really be localhost. It needs to be a domain name that's got a SSL that's trusted by that network or globally as a proper CA. And then we make a call out to it using just a standard client. And this is just a post to the URL and comes back. Now the problem with this is that if I run this service on a different port, if I try and run this now in Kubernetes or another DNS or some system somewhere, I now need to change this code. And traditionally this is done by making sure that they're in environmental variables so that we can change them quickly, restart the app and all is good with the world and we only have a little bit of downtime. But realistically, what happens then when you want to load balance? That URL, as we talked about before, now needs to be a load balanced URL. And we're now deciding that we're talking with a load balancer instead of communicating with the system directly. And all of this now requires more work. For instance, just basically the load balancer needs to now know all of the places that this app is running and also needs to support things like HTTPS. And load balancers aren't cheap. So let's Dapprize this. Let's now get rid of this hard-coded URL and let's include the localhost for the Dapr system. Now we said that localhost and we are running on port 3500, which is the port that we started up a Dapr environment. And when we connect to it now, we can connect to our service, but we need to let Dapr know what service it is we're wanting to connect to. As I said before, I wanted to connect to the order processor. Well, I've not provided any URL. I've not provided anything that lets us know what that is. We've just connected to localhost. And we're going to make a HTTP call off to localhost. Well, what is that? Well, to help out, what we can do is we can now give our services unique names. And we've probably already got that within our business. We have unique names for things like purple monkey or green elephant or something. You'll have a name for a particular service. And in this scenario, we're not winning awards for our naming convention. It's being called order processor. So we're telling the HTTP client that because we're using Dapr, I want you to connect to a Dapr app, an application that's been registered with Dapr. And I want it to be called order processor. But what did that look like? Well, this is what happened when we run this. We run Dapr and we register against the Dapr system, and we tell it that this app that we are now going to run is going to be called Order Processor. So if I want to call the Order Processor, I just need to tell Dapr the app ID name that I want to connect to. And now my client is going to still carry on connecting to localhost, but this header is going to get passed along, and Dapr is going to know automatically how to delegate that and what service to delegate that to. So if we give that a run, we should see now that the code works in exactly the same way. And we start making calls out to an order processor, but we don't know where that is. But what's happened here? We've got some kind of error, and it's saying that we weren't able to connect out to this system. There is nothing running on localhost 5000. And if we look, that was because we've got this running on 3501, and we didn't actually run our app within the Dapr wrapper, if you like. We just, because I'm running it here just in Rider, it just run the .NET run. But actually we need to make sure that we run this now within the Dapr ecosystem so that it's able to communicate with each other. And these Dapr services are able to interconnect and talk to each other and share information. So without that, we still didn't know where the app was. So let's give this a run and see now if we're able to communicate just using the name. And we are. We are now making calls out just using the name of the service instead of the URL, and we're using Dapr to communicate with each other. So as a quick experiment, what I want to do is run the order processor again, and hopefully that will fire up. Yeah, that seems to be running. And I'm going to create another shell, and I'm going to run, but I'm going to run it as a different port. Now I'm going to have to change this for this to run, otherwise it's not going to be able to bind. But now we've got hopefully 2 running. So now when I run my order system, my checkout system, I'm going to ask to check out and complete 10 orders. But what will happen is, as these orders go out, they'll get delegated. So 3 is being done, now 5, possibly 7, then 9, and we should be done now. And we can see that the other one has done 1, 2, 4, 6, 8, and 10. So it's been a somewhat round robin system as it's delegated the requests to each system. And as this one has become under a little bit more load, it's delegated it to the other system. So we have locally implemented load balancing just by using Dapr alone. Done nothing really clever. It was annoying having to change that, but obviously if I was running this within Docker Compose or something, it would have been child's play. So this shows how I was able to get an application called the checkout system, make it so it's not aware of what it's connecting to, just that it's going to try and call some system called order processor, and it's not even aware that this is being load balanced or how many instances there are. If at some point we come under load, so let's say it's Christmas Day, or well, coming up to Christmas should say, and Black Friday as we get, then we can just extend the amount of containers or infrastructure that we've got that is hosting these things, and all of our code just works. We as developers don't need to be cloud engineers and DevOps champions. We just write good quality code that does the job well, and when it's dropped into a system, it works. Here's my code, run it, I don't care how. So I'm really hoping that you like this type of video where we talk about, although Dapr does service invocation what does it actually mean? Why is this even a feature? For some of the champions out there, you're going to know what this is, but there are still a lot of people who are coming into this who don't understand the technology, the reasoning behind these things, and they've not felt the pain yet. They've not tried to get load balancing set up. They've never been in a scenario where they have one is none and a service fails, and it's Black Friday and your boss is screaming at you because they're losing money per second. This is a real solution to a problem, and although, like I said, it has been solved before in other frameworks, I personally don't think it's been solved in such a great, elegant and simple way, and I truly believe that. This system is incredibly simple for even me to understand. So if I can do this, if I can call this system and get load balancing set up within a couple of minutes, 20 minutes or so, then it means that developers who are just wanting to write good code don't have to spend the rest of their lives watching Pluralsight, which is a great system, but watching Pluralsight on how to get my container loaded into a cloud infrastructure using Helm charts and Kubernetes. We can just write good code and get it to run. And I want to say thank you to Dapr for this. Now, there's more to come. We've only just hit the surface of Dapr with Service Invocation. We've got more videos to come. So please, if you're interested in this type of stuff, hit the like button and also subscribe. But thank you very much for watching.